Distinguished guests and leaders, hello everyone. I am Sun Peng from Trina Storage. Today, I would like to share with you some of Trina Storage's past practices, as well as our case studies regarding AIDC, AI data centers. First, let's look at a set of data from the International Energy Agency, IEA. As we can see from the chart, the global power production structure is undergoing rapid changes between 2015 and 2035. The proportion of traditional fossil fuels, what we call coal and natural gas, will continue to decline, while the growth rate of wind and solar energy is accelerating. By 2030, the penetration rate of renewable energy will rise to 43%, and the proportion of wind and solar power generation will double to 28%. The entire trend presents a double high characteristic: high renewable penetration and high power electronics integration. With such a massive integration of new energy and high ratio inverter-based resources, this transition means our power system is gradually shifting from the traditional source grid load model to source grid load storage. However, this massive integration also brings certain challenges. As shown in the middle charts, when the proportion of wind and solar generation in the grid exceeds a certain threshold, the inertial support capability of the traditional grid drops sharply. As is widely known, grid stability is determined by voltage, frequency, and phase angle. Looking at the bottom two charts in the middle, first, the frequency response curve is showing a deteriorating trend. Second, voltage fluctuations are also intensifying. At this stage, the grid requires a new solution to actively construct grid stability. This is the value of grid-forming GFM storage. As seen in the third section, compared to other grid technologies, grid-forming storage offers the most comprehensive grid support. It can provide long-term, active, and reactive power support, realize islanded operation, and enable station-level black starts. Theoretically, it can replace synchronous condensers, cameras, grid-forming SVGs, and FACS. It is important to emphasize that grid-forming storage not only leads across the board in technical specifications, but also offers significant advantages in engineering costs and construction cycles, providing an optimal balance between technical feasibility and economic viability. Trina has a vertically integrated layout regarding grid-forming technology. Globally, we have 5 major research institutes: Battery Research Institute, our Cell R&D team; Storage Product Research Institute, focusing mainly on the development of our large-scale storage products; Advanced Integration Center, focusing on the integrated application of PCS, power conversion systems, and storage; Power Electronics Institute, covering PCS and MV medium voltage systems; System Research Institute, focusing primarily on grid-forming technology. Globally, we have over 600 R&D personnel and more than 100 authorized patents. We have also participated in the formulation of over 20 standards. Regarding grid-forming standards, Europe and the US began exploring regional specifications in 2020. By the end of 2025, China is expected to release 2 national standards related to grid-forming storage. This marks China's transition from a technical participant to a rule leader in standards. China's standards aim to have power stations support the main grid, with a core focus on fault ride-through and reactive power support. The UK standards require power stations to engage in active regulation, similar to traditional power plants, maintaining system-wide frequency and voltage stability, focusing on primary frequency regulation and dynamic reactive power control. Australia's standards focus on local defense, ensuring that massive distributed power resources do not affect the voltage and safety of the distribution network. Chile's standards focus on oscillation suppression, emphasizing the stability of power stations in weak grid environments, paying attention to damping and impedance characteristics. For our grid-forming platform, simulation and actual measurement are paramount. To translate theory into actual products, we invested heavily over several months to build a full scenario grid-forming platform. This includes a simulation center covering digital modeling and hardware-in-the-loop simulation, and a 20 megawatt-hour empirical test center for storage and PCS testing. Regarding the technical roadmap, in previous years, the basic grid-forming algorithm used virtual synchronous machine (VSM) technology to achieve inertia response and primary frequency regulation. Within the next 2 years, we will achieve power oscillation suppression to further enhance grid strength. In the coming years, grid-forming storage will face more practical issues. With the rapid development of AI, we will integrate AI for intelligent applications, such as seamless switching between grid following and grid forming modes. In terms of product solutions, we offer a full suite ranging from DC containers to PCS and EMS. DC containers. We utilize cells with high thermal stability to support core grid forming demands, including the domestic requirement for 3x overload capability. Our cells support 1.5x to 3x overload with thermal stability protection. To handle such high rates, we selected pack wiring and chillers capable of handling the load. We use higher power chillers to ensure the cell temperature difference remains within 2.5 degrees Celsius. We partnered with UL and were the first to pass the UL VMark certification, verifying this 2.5 degrees Celsius performance. Grid forming PCS. Beyond supporting 1.5x to 3x overload for 10 seconds, we support multi-unit parallel 1-key black starts and station-level black starts. Grid forming controller. This supports off-grid black starts, power regulation of multiple PCS units, and dynamic grid regulation. EMS. Its main function is to coordinate with the grid for electricity market trading, manage on, off-grid switching, and switch between operational strategies. Regarding case studies, we have 2 major examples in Australia and Latin America. Australia. We have a major 500 megawatt-hour project. As many know, obtaining local certifications in Australia is difficult. Trina obtained authorization from AEMO, Australian Energy Market Operator, last year, along with AS 5,139 certifications. Latin America. This is the Atlas 1.3 gigawatt-hours project, the largest grid-forming project in the region. The grid in Chile is extremely unstable, forming a typical isolated grid environment. Trina provided high-efficiency solutions, achieving station-level black start, sub-100 milliseconds grid support, loaded black start, and seamless switching between grid forming and grid following modes. Finally, regarding AIDC, AI data centers, we have seen rapid development recently, such as the Sanjiangyuan project in China, realizing green power absorption. In North America, there's also a demand for data centers to access green power distribution. AIDC faces challenges such as high power requirements, unpredictable loads, and power quality issues. Trina's solution pairs PCS with storage to create an 8-hour long-duration storage plan. Through grid-forming technology, we achieve seamless on-off-grid switching and ensure stable power quality. Simultaneously, our storage system utilizes a string architecture, one cluster, one management technology, which improves throughput over the lifecycle and ensures system uptime. Lastly, our AI prediction function uses the latest AI technology to accurately forecast and assist in better green power absorption. That concludes my sharing today. Thank you, everyone.